Dear students, in today's video we are going to discuss electric potential due to a point charge. Let us start with one more question which can appear in the exam, that derive an expression for the electric potential at a distance r from the point charge plus q. What is the nature of this potential? For that, we take a point O where we have mounted our charge plus q. P is the point at which we want to calculate the electric potential. This point P is present at a distance r from O. Then we choose a point A where the test charge q0 is present, and this point A is at a distance x from point O. Dx distance is travelled by this charge q0. When this test charge q0 move from point A to B, it travel a distance of dx. Then we apply Coulomb's law between the charges q0 and plus q. We know that the Coulomb force is given as F is equal to 1 upon 4 pi epsilon naught q naught divided by x square, the distance between the charges. X is the total distance between the charge plus q and q0. dw is the amount of work done. So it is given as dw F vector, the force, electrostatic force, into dx. Dx is the distance between the point A and the point B. So the distance is travelled in this way, while the positive charge plus q has force in this direction. So the force and the dx are on the same line. So the angle between them is 180 degree, and cos 180 degree means minus 1. So dw is equal to minus f dx. Then to find out the total work done in moving the charge q0 from infinity to point P. From this infinity to point P, we take integration of that small amount of work with the limits varying from infinity, means we have started the journey from infinity and we are reaching toward the point P, which is at a distance r. So the limits are from infinity to r. Minus f dx is here. We substitute the value of f from the Coulomb's law and dx along with it. The integration is for the dx only. So this q0, 1 upon 4 pi epsilon naught, all terms are constant. They can be taken out of the integration. Only x square, 1 by x square, remains inside the integration. And we know that the integration is the power increased by 1 and divided by the power which appears after increasing by 1, right? On simplification, we get this thing. Then we substitute the upper limit first, that is r, and the down limit is infinity. So it is 1 by r minus 1 by infinity. 1 by infinity turns out to be 0, right? 1 divided by infinity is 0. So this term will vanish. Only this term is left, that is 1 upon 4 pi epsilon naught q naught by r, right? This is the expression for electrostatic potential. So this is the amount of work done in moving the test charge q0 from infinity to the point P. So this is the work done. We know that the electrostatic potential is the ratio of work done divided by the test charge. So when you divide with q0, this will not appear in the expression. So V is equal to 1 upon 4 pi epsilon naught q by r. So what is the nature of this potential? This potential varies inversely with the distance. If you have a source charge here, then the potential has value higher when the point lie closer to the source charge. As you move away from the source charge at the infinity, potential will be equal to 0. More closer is the point of observation to the source charge, higher is the potential. As you are moving away, potential is decreasing. Secondly, electric potential is a scalar quantity, because we know that V is equal to W by Q0. Charge is scalar. It has no direction. Charge is scalar. It comes as per the quantization of charge. We know that Q is equal to NE. N is the integer, can be both positive or negative. E is the charge on electron, so no direction is associated with the charge. It's a scalar quantity. While work is the dot product of F vector, force, and the distance. So dot product of two quantities always gives an answer which is a scalar thing. So electric potential is a scalar quantity. Note this thing, electric field is a vector quantity. It has a direction, while electric potential is a scalar quantity. Next, it is spherically symmetric, and the electric potential at infinity is equal to 0. This is all about today's video. Thank you.